Well, hi, good morning. Thank you for joining me in my shop, keeping me company while I work on this radio. Today is July 13th, 2023, and I've just been sitting here for a few minutes wondering, well, what should I do next? I'm in the capacitor replacement mode of the repair right now, and one idea I have, I think I'm probably going to do, is replace the big fat capacitors, the paper ones that are big and fat. There's one. It says 0.1 microfarads on it. That's a large capacitor. There's another one hidden from view in behind this blue capacitor. There's another big one back there. So what are these capacitors doing? Oh, I've already taken a look. Let me show you how I did it. Took this very handy diagram. That capacitor is number 30. And look upon the schematic. Show me number 30. There it is there. It's not where I thought it would be. These 0.1 are large capacitors, usually one in a radio like this. There's two in this one, interestingly enough. Usually they're on the screen circuit, and their job is to quell any signals that are traveling between tubes using their common screen connection, screen supply connection. This one is on this line, which is going up to the grid of the first amplifier. So its job is to ensure a zero signal here, or provide a signal ground at this point in the circuit, rather than down through here, which kind of looks ugly just looking at it. So they're using a big capacitor, which means that it's a challenge to do what they're trying to do here. So if this big capacitor is weak in terms of capacitance, if it doesn't have the capacity it once had, what would happen? Well, I think some of the signal that's making it onto this grid line will begin falling across these resistors way down here, and that wouldn't be good. That's about all I'll say there. The real idea is to make the signal that's being applied here be entirely across this resistor here. Okay, that's what that guy's doing. What if it's leaking DC? So there isn't much DC in this part of the circuit. There's no couple hundred volts or anything like that. It's just going to be a few volts negative to provide a bias on here. Looks like the bias is provided by the signal itself. It's a self-biasing arrangement, I think. That's what that is. So if there was a leak, well, you got a million ohms sitting here. So leaking, tiny portions of coulombs down this way, I just don't think is going to cause much effect. This is probably not too important if it's leaking. Could be wrong about all that. It depends how much the leak is. I'm always thinking microamps and tiny amounts, not significant amounts. Okay, where's the other one? The other one's here. It's right here. It's number 14. Lucky number 14's right in the middle, right there. And this guy is hooked up to the screen circuit. So his job is to zero out any signals that might be sitting on this line and get rid of them. If he fails in the mission and cannot keep this line basically zero signal, then some signal can travel from this tube back to this tube, and boy, that looks like some kind of oscillator to me. And there's maybe even more consequences if we follow this line down here. No, maybe male. Where's this guy getting its voltage from? It's grounded over here. Gotta be coming from this way. It's supplying to a plate up here. And looks like it's getting it right through this resistor here. This 10,000 ohm resistor. And looky there. There's another Now, is that the one I couldn't find? Didn't I reason out there were 4 in this radio? 4 physically in the radio. 1, 2, 3, and 4. And I got 1, 2, 3. Didn't I see another one in here? I've lost track of it. Okay, will remain a bit of a mystery. 3 or 4 electrolytic capacitors. Okay, as a side story, back to the main story. So this is where the supply is coming in. This way. So dot there, so it's connected over. And this is the filter capacitor for this line going up here. What's the 0.1 doing? 0.1's on the other side of this. 10,000. We actually have a supply voltage at 10,000 ohms, 10,000 ohms, and 50,000 ohms. We're just adjusting the voltages here a little bit. A little higher voltage on this side going to the plate, and the other side a little lower voltage going to the screens. That's normal. And this plate gets its voltage from the other side of the filter here. It gets a more filtered voltage here. Going up to the plate here. And this guy's probably got a puny plate voltage. Right. That looks... I don't know what's going on there. Okay, enough talking about that. Enough, because I have... occasionally I say things that aren't particularly true, and I don't even realize it. Okay. That's it. We're going to do those 2 big capacitors and see what happens. Do them one at a time. Check the radio afterwards. Why bother with that? Because the 2 capacitors are doing very different things. I don't know if that makes sense. It doesn't even make sense. Okay, I'm going to go drink some coffee and then we'll start, warm up the soldering iron and get going. Okay, I'm going to go after this one first, and I want to see clearly where it's connected. It's hidden behind this blue capacitor, so I have this camera aimed at the end there. We can take a look. And what am I looking at here? So you cannot see the capacitor, the target capacitor at all, but I can bring the stick down here. I'm pretty sure it's this terminal here that it's connected to. Maybe not. Just trying to see the end of that capacitor. My view is blocked by this. What is that? I never really noticed this big white thing here. Well, I could guess it's a capacitor of some sort. But it's kind of in the way. I can't get right back down here. See clearly where the end of that wire's going. It's got to be going to that terminal right there. What am I looking at here? Very strange looking, but I think I see the wire coming right out. Going right to that terminal there. That's got to be what it's doing. The reason I'm cautious is because, if you've been doing this work for a while, you've probably cut the wrong wire a few times, and every time it's very disappointing when it happens. So what we'll do is we'll cut this one, this end here. That's going to a ground terminal, is it? ground terminal there. No, no, it's a terminal on a terminal strip. It's not grounded. Okay. There's one end. Get a hold of it. It may be easier to see the other end. For some reason, it may be easier. No, just can't get around. Okay, I'm going to shove the cutters up in there. Oh boy, how am I going to get the cutters in there? I may have to take this big one out of the way. It looks like they've just wrapped this wire around once. That's all I'm going to do. I'm going to have to pull this guy out, I think. Or maybe I just bend them up. Just bend them up. Yeah. That's easy. Well, there we are. There we are. Mystery solved. Okay. And we'll go in and get that. And this thing where the outer foil marker is showing at this end. Whoops. Got it. There we go. Okay, come out. There it is. That's good because the freezing was just starting to wear off. 0.1. Really? Do you think you're a 0.1? Let's do a little experiment here. And we will measure the capacitance of that. My experience tells me that when you measure the capacitance of a leaky capacitor like this, you get a higher reading than what's real, often much higher than the actual number written right on the capacitor. So this thing says it's a 200 nanofarad. That would be a 0.2 microfarad, and it's supposed to be a 0.1. You can see ESR is fairly high, and the loss is 5%. Well, the high reading, I think, is really coming from the leak of current through. I don't know this for sure, but what am I doing? The current leak through it. And the testing device is designed on the basis of there's no leak, I believe. But that's just what I believe. So I'm going to give it this guy here. This guy will also measure the capacitive value of capacitors. I don't normally do that. I use the other instrument. It's much better, I think, than using this one. But this one's accurate too. But normally, I'm really interested. I'm throwing capacitors out and I'm testing them on the way to the garbage can, basically. So I'm not too interested in their actual capacitance. I'm more interested in their leakage. So here we go. We're on the 50 volt scale, and it's a big capacitor. It takes a bit to charge up. So that's about not quite a third open. And of course, if we go up another step in voltage, it's never going to open. There's just too much current leaking. So typical. Okay, so I have to put a 0.1 in there in place of that. Okay, that's what I'll do. 0.1, that's a big capacitor. 0.1, and the voltage, let me just double check this. The voltage here. I think this guy's, no, this was the this one. So there's almost no voltage here. It's going to a grid. Yeah, so I could put a low voltage capacitor there, and the one I just took out of there, I think it was a 200 volts. So that's about as low as these capacitors go. I don't think they made them much lower than that. Okay, so it's probably only 5 volts in there. Good. And we'll find something to put in there. 0.1. Okay, you can see the camera right in front there. That's what we're looking through now. I don't normally video my soldering anymore, just in order to speed up the videos, both for me doing the work and later doing the video work. Soldering's a little bit boring, and I'm not a master solderer, believe me. I can hardly see what I'm doing. Actually, the view in the camera is excellent compared to what I've got from my own eyeballs here. It's a big terminal. Something's cooking. Probably means moisture, that bubbling there. Some kind of gas is coming off of something. A little more solder. So I shouldn't do it for too long. It's already too long. It's just wires here, though. I think that's going to do it. A little smoky. Okay. Now, that's one end. We got to get to the other end. Okay, keep the camera going here. Looks like I got way too much wire though. Preserve the wire as long as I can. What are you seeing on the camera there? Oh, you got a nice view. Like I'm looking from the end of my arms here, not down where my hands are like you are. Soldered. Okay, let's get the solder in there. It's a little crowded with the camera where it is. Okay, there we go. Melt. Solder the solder. Oh, I'm burning some plastic here. I'm burning the blue capacitor. I can't get the solder to go down there. On the back side. The camera's in the way. Okay, wait a second. A lot of smoke. There it goes. There we go. I got it. Don't know how much of that you saw, but one's in. I think we should test the radio in this case. And what could we expect from that? More volume, like louder, better tonal quality, but we're not going to be able to really discern that, I don't think. But we can certainly turn it on and give it a shot. But I'm going to have a little coffee first. Just before I start the radio up, I thought, well, why don't I identify what this is? You know, it's probably a variable capacitor of some weird sort. There's one here. This is definitely a variable capacitor here. And on the other side of this radio, which well, maybe I can spin it around this way. If we look, okay, let me get my fingers on it here. It's down here. If we look, okay, down, give me something to point with. Point with this. Down here, there's an adjustment. That's that upper capacitor, and then the strange white block is right here. There's two retaining screws here and here, and then this one got to be an adjustment. Got to be an adjustment screw. So two. Remember that number. 2. That's 2 ones. There we go. So we look here, and we see, for instance, this capacitor just replaces number 30 down here. There's a tube socket there, tube socket there. There's a square thing here, square thing here, and then there's this thing, the tuning capacitor here. Where is it? Where is it? So we have this capacitor here. And we have this, looks like a resistor. It's shown. It's shown at around this thing. Wait a minute. There's only one here, and there's 1, 2 here. So something funny's going on again with this radio. See, there's supposedly a component right here. That would be either up in here or in between somewhere. I don't see it. There it is, right there. That's it, right there. No, that's not it. Yeah, that's probably it, right there, that one. And that's coming to this. So they don't show the wires on here, but it's probably coming to this. What is going on? This has 1, 2, 3, 4 terminals. This has 1, 2, 3, 4 terminals, and this other thing is just the thing with 1 terminal. If you look at this, this has a number on it, number 7. This thing into number 7. Number 7 says Compensator Dual Model C9. And then below it, it says again. Oh, there's a 7A here. Compensator Model C7. 1500 kilocycles. So they have one variable capacitor. They're calling it a compensator. This way. Got the paper turned sideways on my head too. So there's a 7, an unnumbered line underneath it, and then a numbered line 7A. 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 Can we find these things in here? 7A, right there. My eye just went right to it. Used in model 38.7 only. That's the ground connection here. There's a big X there. What would the X be? What would the X be? So that's 7A, then there must be compensator number 7. It's bound to be right around in this area here. There. Wait a minute, that's a fixed resistor there. Fixed capacitor. Is it? And all this is in the, what I imagine is the oscillator circuit here. 7, and that's what we're looking at here. 38.7, 38C7. We'll drop the C. Well, okay, so I think what it is there's a capacitor that's in parallel with the tuning plates, and that's a typical trimmer, and then there's another one that's in series with the tuning plates, and that's a pattern used on the lower frequency end when you're making adjustments. So you can move both ends of the band around. You can do this kind of thing, whatever is required. Whereas if you just have one adjustment, all you can kind of do is kind of stretch one end a little bit. So I think that's what's going on there. Want to be in parallel, want to be in series. Why all these terminals here? There's a lot of terminals. There's not 4, there's only 3. 1, 2, 3. Oh well, I don't know. Maybe one of them is a ground. It did call it a dual. Called it a dual. Maybe originally it was a dual, and they had trouble with it. Oh, wrong spot. C7, C7, C9. Oh, look at this. Compensator dual, model C9. Then below it, compensator 580 kilocycles, model C7, and then compensator model C7 1500. So that's what they've done. The 7A is for the 1500 end. And on the 7, well, we'll figure it out, I guess, when we go to do it, just which one's which. Because it's not clear which one's which. Okay, kind of jumping ahead there. Let's start this guy up. I have to sort that stuff out sooner or later anyway. And volume down, band switch on AM, no antenna connected, switch is off, put it on, and we'll apply power. Here we go. The power is happening. The power. Just reading a little bit of history on Canadian radio. And are you a Canadian? Then, if you're a Canadian, you should know the name Fessenden. I'll bring his picture in here if I get a chance. Fessenden, Professor Fessenden, Canadian, who tried his best to ply his trade here in Canada, but was beat out for attention from the government by Mr. Marconi, who was a very, very good promoter and managed to steal the show, basically. But if you look into the history of Fessenden, Fessenden has all the major firsts in radio. First voice broadcast, first time broadcasting music and entertainment. He was doing it to banana ships out in the Atlantic Ocean, I believe. A lot of firsts, but his name, Fessenden, is not known. He's forgotten about. Yet, he's probably... If he'd gotten the same traction and interest shown to him that Mr. Marconi got here in Canada, we'd be talking about Fessenden, and we would not be talking about Mr. Marconi so much. Okay, the radio's got to be warmed up. I'm not hearing anything. Turn it up. She's silent. Okay, no antenna. So we'll stick something on. What it'll do? We'll stick on the real antenna here that goes outside because. Come on, radio, better make some noise. Oh, it's almost nothing. Yikes! That's really not what I'm after. I'm really after a lot more volume. Did I hook this up to the right spot? Well, it is what it is at this point. We have very little volume. Wow, I seem to, sometimes you work on these radios, they get weaker and weaker as you go. It sounds exactly the same. That's a little surprising. That's a tone control, Jim. You're moving the tone control. There. Short wave. Let's go to that 9 megahertz signal. That's right where I am, right in this area. Anybody hear that? I hear it. That's probably 9.330. Just about the strongest station you're going to get. Looking for WWV here, but fat chance. Fat chance, fine. This is a very difficult radio to tune. Okay, that's good. That's good. Volume poor. We won't worry about that right now. Back to AM. Oh, that's better. Yeah, I think I don't know what I was doing there. What was I doing? That's better. Pretty quiet down here. Probably just alignment issues. So these noise signals are gigantically strong. So they're making it through the weak radio. Probably all alignment. Okay, we got one more big fat capacitor to do. This guy up here. Oh, I've only got the radio working on 80 volts. That would be one reason why the volume is low. 80 volts is very low to run one of these radios. It's surprising it's working at all at that voltage. Okay, let's take this guy out. Now, could be a charge on this capacitor. Chances are it's bled away almost immediately upon turning the radio off. Pull that out. Let's not make a mistake here. Oh, what have they done here? Oh, for crying out loud. For crying out loud. That's another thing my mother said over and over, and it's just integral to my language here. Hang on. There we go. What have they done? This side, for some reason, they've wound the wires together on the capacitor and the resistor. Why? Well, you see how they've insulated it with a tube. Could be they felt they had to insulate the two wires, the one coming from the resistor and one coming from the capacitor. And if they twisted them together, they could do it with one tube. Bob, we're going to save 0.1 cents per radio, 10,000 radios. Well, that's $50 in your pocket. So we should check this resistor too, I think, because maybe it's due for a change. And then we have this, oh, that's a big resistor. Look how it's all kind of burned off the surface. Looks like it's white hot in the camera, doesn't it? But I'm sure it isn't. Well, let's check this resistor. So if we do the body and dot thing, body looks black. No, body is orange, end is black, and the dot, good grief, who knows? So that could be one. That could be a 10,000. That could be a 10,000 ohm resistor. You sort of jump to that conclusion because it really doesn't matter what I think, does it? So we will look. Let's investigate this. We'll use the information we have. Here we are. Resistor we're talking about. And capacitors right here. The resistor number is 16. Part number is 16. Resistor 10,000 ohms, 1 watt. Okay, so we're going to check it and see, is it really 10,000 ohms? Now we'll try using this instrument because it's right here. It's right here. And we'll see if this guy will do it. This is really quite the thing. See, every time I use this, the rest of my equipment gets anxious. Look at that newfangled guy. He's got a mind of his own. He can think things through. It says it's a capacitor. That's not a good sign. It's taking a long time. 30 picofarads. That's tiny. 30 picofarads. So why is it telling me that? Can I hook it up to the wrong thing here? 30 picofarads. So open resistor? No, it couldn't be. Could it? Could it? Oh. set this thing into some weird... Oh, it's got all these weird settings here I never even noticed. Never had that. Rotary and... What? Rotary. I'm going to just leave it alone. Leave it alone, Jim. It'll just turn itself off. Got it into some kind of a calibration mode there. Okay. This resistor, let's use the classic ohm meter. I don't know. Is this a classic now? Can you call these a classic? 10,000 ohms. Are you anywhere near 10,000 ohms? So we'll try that right on the wire here. Trouble connecting. 10,000 ohms. So what that other instrument was doing, it works on an entirely different principle, and apparently didn't work well in this case. The first time that thing's really been way off. So that resistor's good. We're going to leave it. It's just a matter of changing this guy, and we could attach it right here, or we can go down to the terminal. Probably down to the terminal. Is there some reason why they want this capacitor connected right to the output of this resistor and not have any wire? I don't think so. It's a Philco 400 volt capacitor. Come on over here. Smart enough to leave my tester running. How about this guy? Volts. Okay, watching the eye. Wow, it's coming right open. That's impressive. 150. It takes time to charge the bigger capacitor up, but it's just starting to open. You can't see it, but I can see it. So yeah, it's definitely leaky. How bad though? Just giving it a moment to discharge. Let's do something a little odd with this guy here now. What odd thing can you do with a capacitor? Well, one of the things you can do, you can look for charge remaining in the capacitor. There can be another thing going on. Let's see. This isn't really the worst thing. I'm kind of just goofing around here, really, frankly. So we're going to put this on 600 millivolts DC. Might be some residual charge left in here. Overload. 6 volts DC. So expect that voltage to come down as you bleed away the charge. So what we're going to do, we're going to help it out here with a clip lead. Put this clip lead on, set this guy aside for a few minutes. I'm just going to discharge completely, and then we'll continue the experiment in a bit. In the meantime, I'm going to put a 0.1 in there. Now in this case, this guy is sustaining a high voltage. It's right on the screen line here. There could be a couple hundred volts, some radios even more on this line, so this capacitor's taken. So I got to make sure I put a capacitor in there that's good for the voltage. 0.1. That's tricky. A 0.1. I don't think I got. Well, look. I got something somewhere. Okay. Last other connection. take a look at that more closely. Okay, let's do that. Grab the other camera. It's good. That could be a little bit better. Yeah, that one could be a little better. So, now this radio is not exhibiting any signs of a weak, what would normally be called a decoupling capacitor, which is the one I just replaced. I like to think of them more as silencers or capacitors providing a signal ground. I like to look at it that way a little more. Soldering to an old wire here. Okay, that's much better. I can see that with my eyeballs. Okay, there we are. That's a nice 0.1 600 volt capacitor there. It's going to do the trick. Ready to operate the set again. Volume down. Turn it off. Switch it on. Are we ready? Hang on a second. I'm going a little too quick here. Anytime we want to power stuff on. Oh yeah, I got this experiment to do. Let's do this experiment just before I power on the radio. I'm not saying what it is yet because it's probably not going to work. It's probably what's I'm going to get a malarkey here. So the capacitor should be at a 0 point with these clip leads on here. Zero. Okay, no surprise there. Take this off. The capacitor should not, well, if you don't discharge it long enough, the capacitor can redevelop its charge because you actually didn't discharge it 100%. With a little bit of time, the charges will separate again and show up on the leads, and you can read it with a meter like this. But this meter will draw a tiny charge out of a capacitor like this pretty quick. So you watch the meter, see if it doesn't give you a big number, and then go down. Let's see what happens. So there's a whopper of a number. That's minus 0.2, minus 0.1. Now here's what I'm going to tell you. It's not going to go to 0. It's going to stop short of 0. I mean, it should have just plummeted right down to 0. Just slowing down. We have to hold this for quite a while. So I would guess it's going to settle out around 70, just based on the way it's going down. What this is going to do is it's going to stop somewhere. Oops, I lost connection here. We don't want that to happen. As soon as you lose, well, here's another thing. Suppose I take away, whoops, it's gone to 0. There we are. I just did an experiment. So we're at 130, 120. If I take this away, so the meter's not connected, and I reconnect it, 160. I'll go back down to 120. What is happening here? Now this is not, I'm suggesting, this is not residual charge. This is the capacitor turning into a battery. Yeah, it's not going to power your electric car, I'm afraid, but I got my finger on it by accident. So I took it off again and put it back on. You see it's chumped up again? My fingers can generate a voltage here if I'm not careful. So it's hanging around 100. No, it's still going down. So sooner or later that's going to settle out at some, if I clip this on and left it aside, it will settle out at some number like 70. Looks like it's going to settle out higher actually. And this thing's a battery. It's become a battery. It's mixed metals in here. Aluminum foil, maybe steel leads. The steel leads may be plated. They may be copper leads. They may be plated with something. So you have mixed metals in here. Now, if there's 0 moisture, it wouldn't really matter. But see, it's not 0 moisture. Now I'm going to take this off. You see, it's 94. I'm going to put it back on. And see, it's gone up again. because as soon as I stop bleeding the charge out, the charge begins to build based on the battery. And the open circuit voltage here will have something to do with the metals involved. You know what the it's electromotive force. To me, it's the electron pressure in the two metals is not the same. And when you touch the metals together, the electronic pressure makes it uniform, and this delivers the pressure into the electrolyte. And then the electrolyte becomes, chemistry starts happening basically at the interface of the metal and the electrolyte. Sometimes generating gas or whatever it might be that's going on. Some kind of chemistry takes place. This is a 100 millivolt battery, but you can't draw any current off it. Well, I can draw enough current to run this meter right now. Well, not run the meter, but you know what I mean. Operate the sensing circuits of this meter. Now I have another meter whose input impedance is 120 megohms. That would be interesting to try that on this. Maybe we'll do that experiment. See what happens. Okay, back to the radio. We're ready to turn it on now. After doing my experiment. Power on. Yeah, the last thing I'll do today is I will measure that same voltage, the 100 millivolts, using a meter that draws almost no current at all. So it won't remove the charge from the capacitor plates so much. Are we operating here? Yeah. Volume. Antenna. That's what's missing. We're missing the antenna. Okay, volume back. Antenna on. Don't like it when you turn on the radio and it's quiet like that. There it is. We certainly don't have the proper volume. This is full blast, and it should be screamingly loud. It is not. Next, short wave band. Oh. Hey, you know what? We're still at 80 volts here. Full voltage. Give her. Lots more volume.
I say, Lord God in the highest. So let me say at this point again, please be patient with me.
And now, I'm going to teach you something. What's a high crime? Okay, in the American system, they talk about high crimes and misdemeanors. And I've always wondered, what the heck is a high crime? Here's what a high crime is. A high crime is any crime committed by a guy in a high position. Like the king, who of course is his highness. High crimes are crimes committed by people in high, powerful positions. That's a high crime. Here we go. That's the end of the lesson. Okay, we're going to do that capacitor voltage battery moisture check. So I just turn that off. Very good. Okay, I'd get that set up just a bit, and then we're done. Okay, so you see the meter there. It may still be warming up a bit. So this meter's input impedance is like 125 megohms. It's really, really high. The soldering aren't running anymore, and so I have the leads here, the capacitor. And when I clip this onto the capacitor, the meter should show it. You know, it's warmed up enough. The zero is, oh, it's so sensitive. So here we go, putting it on the capacitor. Okay, now you notice it's gone up and it's falling very, very, very slowly. We're on the 3 volt scale, so it jumped right up to 1.5 volts. 1.5 volts. Now you got to ask yourself, if this capacitor were in a position in a radio, could it, in just the right position in a radio, could this voltage push a grid voltage around? I kind of don't think so. But it's just interesting that these old capacitors have this characteristic, and my guess is, it's not really a guess, but if you take a brand new capacitor, we'll grab one here. Okay, this isn't even brand new. This is actually a vintage capacitor, but it's never been in. anything. Would there be any voltage here? Hey, what happened? Where'd it go? Oh, it's just the lead fell off. Here we are again. Okay, so what kind of voltage might be on something like this? There shouldn't be anything, right? There should be nothing. There should be nothing. Well, I'm going to have to eat my hat here. It looked like there was a momentary... Now that could be a charge, maybe by me touching the leads briefly, because of electrolytic action against your, I'm on electrolyte, right? And so just touching the wrong thing in the wrong way there could sort of pump a charge out briefly. So for a moment I turned these leads into a battery and ironed the electrolyte, and then the charge is sitting in the capacitor but slowly bleeding out through the meter. So that's what a good capacitor should do. Not show you a voltage. Now, did I spin this around? Maybe it's going to go the wrong way. No, there it is again. There you are, proof positive. You can see it says 3 volts right there. And that's the end of the video after demonstrating that. It's a few times I've demonstrated this effect. I suppose you could look for that voltage and judge the condition of the capacitor, perhaps. All part of the same picture, really. Well, thanks a lot for watching today. Tomorrow we have a few more capacitors to do, and these are in the radio end of things, I think. They're up in this area. Isn't that the radio end? It's just the blank area. Actually, not so much. Well, kind of the RF part is through here. So yeah, there's the capacitors up in here. Okay, another one you just noticed hidden in here. Yeah, okay, I'll worry about that tomorrow. Thanks a lot for watching today, and by the way, the weather here, we had heavy rain all night long, but my guess is the sun is almost shining outside. That's where I'm heading. See ya.